Welcome to our video on circular motion and oscillation. Today we're going to explore how circular motion is closely related to simple harmonic oscillation, like that of a mass on a spring or a pendulum. This connection reveals one of the most beautiful insights in physics, that the seemingly different motions are mathematically equivalent. Let's start by visualizing uniform circular motion. Here we have a point moving around a circle at a constant speed. As the point moves around the circle, it maintains a constant distance from the center. This distance is the radius of the circle, which we'll call A. The position of this point at any time can be described using trigonometric functions. The x-coordinate equals a times the cosine of omega t plus phi, and the y-coordinate equals a times the sine of omega t plus phi. Here, A is the radius of the circle, omega is the angular speed in radians per second, t is time, and phi is the initial angle or phase constant. Now, here's where the connection to oscillation becomes clear. Let's focus on the projection of our moving point onto the x-axis. As our point moves around the circle, its shadow or projection on the x-axis moves back and forth. This back and forth motion is precisely simple harmonic motion, the same motion we see in springs and pendulums. The position of this projection is given by x equals a times cosine of omega t plus phi. This is exactly the equation that describes simple harmonic motion. Let's look more closely at the key parameters in our equation and what they mean physically. The amplitude, A, represents both the radius of the circle and the maximum displacement of the oscillation. The angular speed omega is measured in radians per second and determines how fast the point moves around the circle. This directly relates to the frequency of oscillation. In fact, the frequency f is related to omega by the equation f equals omega divided by 2 pi. And the period t, which is the time to complete one full oscillation, equals 1 over f, or 2 pi over omega. Finally, the phase constant phi determines the initial position of our point. A different phase shifts the starting position of the oscillation. Let's look at some real-world examples of oscillatory motion and see how they connect to circular motion. First, a mass on a spring. When a spring is stretched or compressed and then released, it oscillates back and forth. This motion follows the equation x equals a cosine of omega t plus phi, where omega equals the square root of k over m, k being the spring constant and m being the mass. Similarly, a pendulum swings back and forth in a motion that can be approximated as simple harmonic motion for small angles. The position follows the same equation, with omega equaling the square root of g over L, where g is gravitational acceleration, and L is the length of the pendulum. Both these systems exhibit oscillatory motion that can be viewed as projections of circular motion. Another way to understand the connection between circular motion and simple harmonic motion is through vectors. In circular motion, we can represent the position of our point with a vector from the center of the circle to the point itself. This vector rotates at a constant angular speed, omega. When we project this rotating vector onto the x-axis, we get the position in simple harmonic motion. Similarly, when we project it onto the y-axis, we get another simple harmonic motion, but with a phase shift of 90 degrees. This is why the x and y components in circular motion are related by a phase shift of pi over 2 radians or 90 degrees. Understanding the connection between circular motion and simple harmonic motion helps us analyze many real-world phenomena. In electronics, alternating current follows sinusoidal patterns that can be represented as projections of rotating vectors, often called phasors. In wave motion, whether sound waves, water waves, or electromagnetic waves, the oscillations follow these same mathematical patterns. Even in quantum mechanics, the wave functions of particles involve complex exponentials, which are closely related to the sine and cosine functions we see in circular and harmonic motion. Let's summarize what we've learned about the connection between circular motion and oscillation. Circular motion at constant speed can be described by x equals a cosine of omega t plus phi, and y equals a sine of omega t plus phi. When we project this motion onto the x-axis, we get simple harmonic motion following the equation x equals a cosine of omega t plus phi. The key parameters are amplitude A, the radius of the circle, and maximum displacement, angular speed omega. determines rotation speed and oscillation frequency, period t equals 2 pi divided by omega, time for one complete oscillation, phase constant phi, determines the initial position. This connection between circular and oscillatory motion is one of the most elegant relationships in physics. It allows us to understand complex systems by seeing them as projections or combinations of circular motion. Thank you for watching this exploration of circular motion as oscillation.